Swayam Prabha. Digital India. Educated India.
Kind of learning objectives for Module 2. So understanding the general factors that influence member axial compressive strength, and then how are we quantifying that in different parts of the world. I can see that the Indian standard is based very closely on the Eurocode column strength curves. And so I'll have some things where we can look at the European curves a little bit. I'd like to review different ways that steel members can fail in axial compression. So we'll do that by looking at different potential elastic buckling modes. If I'm picking up on everything correctly, this is something where I think Eurocode often stays silent and say, look, you've been to school, so you know how to calculate the elastic buckling load, go do it. The AISC provisions provide a whole list of different elastic buckling calculations with different types of modes. I believe I'm picking up on the Indian code mainly just focuses on flexural buckling, is that correct? So it's kind of silent about some of the other modes. Oh, okay, so the strength of an angle, a single angle. So kind of touch on some of that a bit. There's the so-called American Unified Effective Width approach, but that's basically comes from Dr. Temon Pecos's work at Cornell and one of your grandfathers here at IIT Madras, Kalina Ryman, was one of the early researchers with Pecos in leading to some of these developments. I'm interested in talking with him when I see him, and I understand that IS 801 is going to be updated soon. I'm curious if that's going to be going more in the direction of the unified effective width approach, which is kind of what we do in America, or the Eurocode approach, where you do effective width calculation more on a cross section, and then you reduce from the cross section using the overall member strength curves with a chi factor. So we'll look at the unified effective width approach a bit. We'll take an abbreviated look under the hood with Winter's equation for local plate buckling and post-buckling strength. I say abbreviated because some of the things there with my class at Georgia Tech, my graduate class, we'll spend a bit more time diving through that, and I can see their eyes starting to glaze over as we go through all these details of the kind of understanding where all these equations coming from. So try to go light on that. We'll apply the American procedures to quantify axial compressive strength of non-prismatic members. So that's something that my aim is, that's actually doesn't take but a small part of our time, but if I can convey that thing that I want you to take away with that, it's not that hard to do a non-prismatic member and to verify it. We'll look at what I mean by that. And then lastly, I think this didn't show up on the slide that I had posted, but there's some stability bracing design things where the American standards go quite a bit more into stability bracing design, and so I'd like to share some things with you, and how that actually the stability bracing design rules in the IAC actually tie very closely to direct analysis method, even though they were developed long before the direct analysis method. Say, oh, look, here I do a direct analysis of this, I get those rules. So we'll look at how that goes. And so the outline here pretty much follows this. So we're not going to do all 7 of these items here before 6 o'clock. That wasn't the intent. The intent today was to maybe touch on 2.1, maybe 2.1 and 2.2, and then we'll look at plate local buckling and some aspects with effective width starting tomorrow. So let's talk about the base column strength equations here just a little bit. So if we look at column test data, typically if we just put it all, test of everything out there on a plot, this is what Dr. Bierhovde did in 1988. You get a nice, lovely cloud that kind of fits under the yield load and the elastic buckling curve on the right. You say, well, okay, what influence? Those are just all simply supported columns, say. But then in general, what happens? Obviously, we know that your end conditions, any end restraint that you have on the columns will influence the column strength. Any end eccentricities, out of straightness, out of plumbness, or out of alignment, your initial residual stresses, all those things are going to impact your column capacity. So now, column strength equations, just to kind of show you through a bit of international history here. So the Column Research Council was very active very early on. We're talking about 1940s and 50s here. And then moving things forward into the 60s, and the American codes kind of picked up on a lot of that. And so the traditional AISC allowable stress design column strengths pretty much came out of that. Those were basically originated in the early 1960s in AISC standards. Then the Column Research Council figured that, okay, I guess people are getting tired of, we're just talking about columns, maybe we should talk about stability of something else. And so, okay, we're no longer going to be the Column Research Council, we're going to be the Structural Stability Research Council. So that happened in the early 70s, I believe. And Bierhovde's work was very involved with that. I think in the similar time frame were a lot of the ECCS developments in Europe, and SSRC, out of a lot of Bierhovde's work, developed multiple column curves, and those were pitched in American practice and kind of fell on deaf ears. The practicing engineers drive the American standards quite a bit, and the practicing engineers at the time in America basically said, we don't want multiple column curves, give us one. And even now, we're in the technical committees at AISC, we are discussing quite intently that, particularly nowadays, that we're looking at instances where we may be looking at, we want to use very high strength steels. You pay a huge penalty if you don't use a different column curve if you go to a higher strength steel. So at least for that, now we at AISC, we have some traction that, yeah, at least we should have maybe two column curves. You can still make arguments for the others, but it's a hard sell in the AISC committees. We'll talk a little bit about the Eurocode 3 column curves. I'm speaking directly from the second generation Eurocode here, the more recent incarnations. And some words about AISC column strength curves that we've already been using some. They've been mostly the same since 2005. So just to show you a few things, the old CRC curve was the formula you see at the top of the screen here, a very simplistic formula. It's based on a tangent stiffness model, just saying straight column, residual stresses in it, I get some reduction in stiffness as I load it up. Okay, what's the strength of that thing? And the early AISC strength curves, allowable stress design, basically adopted that with a variable factor of safety. So, okay, if we have a very slender column, we want a higher factor of safety. So these were the factor of safety formulas. If for a stub column, it basically reduces to 1.67 for the factor of safety. For a very slender column, it was 23/12, 1.92. And so the traditional factor of safety varied like this versus square root of py over pe. And then, okay, let's look at the curves that have been in place since 2005 and even earlier in LRFD for AISC. So this is the form that we've been showing to you, flashing at you a bit. So we have an inelastic strength curve, an elastic buckling strength curve. Elastic buckling strength for AISC is 0.877 of the theoretical. The inelastic strength is this exponential formula that's a function of py over pe. Or early LRFD, that was written as 0.658 lambda squared. And some of the practicing engineers on the spec committee said, we don't like Greek symbols, take that out. So it's py over pe. Okay? I'll explain to you how, we ballot 2 just passed, and the section of chapter F that's basically bringing lambdas into calculating strength of general I section members. It's passed with the next to the lowest pass rate in the ballot, but it met the 70. It had like a 85% threshold. Ballot positive, yes. You have to get over 75%. So some of those negative ballots have to be resolved, but I think at this point we're probably, I think it's a good direction to move to lambdas. We can talk more about why that's a good thing. Obviously that's what Eurocode does, that's what you're doing in the Indian practice. Back to the AISC curves. So the allowable stress strength curve in terms of a Pn over Py with a factor of safety, omega, in it, divided by factor of safety. That's the dashed curve. And so for ASD, same thing, still a factor of safety. So it's a different strength curve, but our current strength curve is the red curve. The old ASD curve is the dashed blue curve. We haven't really changed anything since 1960. Okay, and that's intentional. With some of Dr. Bierhovda's work, I'll show you some things here. So this is the SSRC column curves, and the AISC curve that I just showed you is the cayenne, and then to black when we've got the elastic buckling. And so the AISC curve basically is reasonably close to curve 2P of SSRC, of the SSRC multiple column curves that were developed. These were developed in the 70s. There was a curve 1, 2, 3 before this, curve 1P, 2P, 3P. What happened is the early curves were developed saying, okay, out of straightness of L over 1,000, and then they decided, no, we want to be looking at calculations with a mean out of straightness, not a maximum out of straightness. And based on field studies with some statistics, concluded, well, the mean out of straightness of columns is roughly L over 1,500, not L over 1,000. And so the curves 2P, 1P, 2P, 3P are based on L over 1,500, essentially. And you wouldn't believe, it's very interesting to pull up those papers. So as a very prominent practicing engineer, Mr. Ray Tide, very well respected with Jenny Elsner in the United States, a very major investigative firm, investigates failures a lot. He wrote a stinging paper of this curve 2P is so bad. Look at that look at how much more conservative that is relative to the strength curve we should be using there in the intermediate range. Really? It looks like the same curve to me. But that was the argument. And so, no, we're not going to go to curve 2p. We're going to use this exponential formula. It's a better fit to what we've been using since 1960. And curve 2p, it's a reasonable approximation of curve 2p, but it doesn't have this extra conservatism in it. Well, what about curves 1p and 3p? Well, this is a table that's in the SSRC guide, and so it's basically explains Verhoeven's recommendations. And so if we're looking at cases with lower strength steels, lower than grade 50, this is all in imperial units here again, so less than 345 megapascals yield strength. If it's a heavy hot rolled section, particularly if it's minor axis bending, then you say, yeah, curve 3p is probably the one we really should be using. If we have welded, built up H shapes with universal mill plates, particularly minor axis bending, we really should be using curve 3. Well, guess what? There aren't any producers, any steel producers that make universal mill plates anymore. And so we say, okay, we don't have to worry about that one. Well, what if you're checking some existing structure? Maybe you should, but that's not what the design code is focusing on. So we remove that, and new design in structural steel in the Americas is predominantly always grade 50 or above. Okay, so we're not going to worry about those other ones that should be curve 3p either. And Professor Galambos did reliability calibration with those things taken out. They say, oh, yeah, we can use a phi factor of 0.9 now with that. Now, before that, there was the worry about these other cases, and we had a phi of 0.85. And that was because, yeah, we don't want to be too unconservative with those cases that really should be curve 3. Then you say, well, wait a minute, there's other cases, but if I've got a light and medium weight wide flange section, major axis bending, wouldn't it be nice to use curve 1? Yeah, that's really more representative. But then everything else, if it's a HSS, a square or rectangular tube section, those are usually cold formed. Well, that's curve 2. Circular tubes, cold formed, curve 2. So there's a lot of curve 2 there, and so it's hard to make an argument to bring in a curve 1 to support the other cases, although it is a good argument. Now again, just to remind you of effective length factor, you really all we ever do is you get your load in the column and elastic buckling, you equate that to pi squared I over L squared, you solve for K. Eurocode 3, so here I want to switch to a handout, pinned-in column that has an initial out of straightness. That's a sinusoidal curve with an amplitude of delta naught. Then we can basically say, well, the deflection, the largest out of bending movement that we get from that would be our favorite amplifier now, 1 over 1 minus p over p sub e, that's pi squared I over L squared times delta naught. So now we basically want to say, okay, let's consider writing an equation for when the axial force and the bending moment in an ideal column that has this out of straightness, no residual stress, we reach a first yield, right? And so we'll say now the level of axial load in this pin-pin column, concentrically loaded at the ends, out of straight, we're going to load that up until we get to a column strength. That column strength, P sub n, is chi times py. So chi is Pn over Py. That's ubiquitous in the Eurocode or in the Indian code. And we're going to find a column non-dimensional slenderness, lambda bar squared. Well, that's Py to the Euler load, ratio of Py to the Euler load. So now let's write the interaction equation for the first yield. So we can basically say what it's going to yield when Pn over Py, so Pn being the load that we're applying, you could say, Pn over Py, plus our amplifier times the P delta moment, Pn times delta naught over My. So we're basically saying, okay, you can say, okay, the ratio of applied load to yield stress to the applied stress due to bending to yield stress becomes equal to Fy. So that's what that interaction equation is. Let me know if you have any questions about that. I think I kind of stated that a bit awkwardly, but we're basically just writing an interaction equation for what's the axial force and moment at first yield at a fiber, extreme fiber of the section, right? So now let's replace Pn over Py by chi, and then let's, there within the amplifier, we're going to write that in terms of chi and lambda bar squared for Pn over Pe, and then for Pn delta naught divided by My, we can basically make substitutions and replace that algebraically by chi times the ratio of the area to the elastic section modulus times delta naught. Or to simplify terms, we'll basically say, okay, well, let's take this term, and we're going to call that term eta. So eta is basically A divided by S times delta naught in this derivation. So now I've got a formula that is relatively simple. If we now just look to try to solve this formula for, okay, at what chi value does this equality hold? We do a lot of algebraic manipulations to get it down to this form. We've got an expression here, 1 plus eta plus lambda bar squared. Well, we're going to call that, we're going to replace that by 2 times phi, where phi is the term over here that I expect you're probably familiar with. And then, so we simply have a quadratic equation here to solve for chi. Let's solve that for chi, and the solution for that we want is basically the solution to that quadratic equation with a negative sign or in front of the radical, which we can multiply numerator and denominator by phi plus square root of phi squared minus lambda bar squared. And we find out that when we do that and simplify, the numerator becomes 1, the denominator becomes phi plus square root of phi squared minus lambda bar squared. And what do you know? That's the chi, that's the basic form of chi that shows up in the Eurocode equations. Now, the only thing now that we need to think about here, so that's a very simplistic derivation, where eta would be just the ratio of area to the elastic section modulus times, that's a delta naught there that I wrote. So rather than write eta in that form, we're going to say, okay, we want to use this to be able to curve fit strengths for different cases that where we have experimental results. And so we're going to write eta instead of ratio of area to elastic section modulus times the delta naught. We're going to write it as a term that's an imperfection factor times lambda bar minus 0.2. And then alpha here in this term is what we call our imperfection factor, and we use different imperfection factors to get different column strength curves. And so this is, I believe, an ECCS recommendation of what curves should we use for different cases. So a little bit different slicing and dicing of how we should interpret things than the SSRC table, but some similarities. I mean, clearly, a major argument you can always make is that, yeah, we really should be using a different column strength curve for weak axis bending versus strong axis bending, and that always falls on deaf ears in American practice. But I think there is quite an interest in these days of, yeah, we shouldn't be penalizing high strength steels with a conservative column curve. So that, I think that's going to go somewhere. I think not in 2027 spec though. We're talking 2035. So I'll be long retired then, and you guys can have fun with that if you're designing in the Americas. Okay.
So there used to be weak axis curve and strong axis curve, right?
SSRC has the curves 1, 2, and 3,
Right.
and so for some of those cases, it would basically say, yeah, you should use a different curve for strong axis and weak axis.
Yeah, I remember Dirk was talking about that.
Right.
Video I was mentioning.
Okay. And was he a proponent, or did he just say, okay, yeah, we?
Yeah.
Right. So kind of the same deal of, okay, after a while you get tired of trying, right? You clearly here the hot rolled hollow sections get a nice beneficial curve. Very light weight rolled sections that are more beam type sections get and failure about in strong axis bending for high strength steel get a very beneficial curve, right? And of course, as you're very familiar, I believe the Indian code doesn't have the A0 curve. Is that correct? Yeah, but has the the A, B, C, and D, if I understand it right. And that's the way we have it. Yeah, again, I think there is a justification for multiple curves, but in American practice, most practicing engineers basically say, yeah, I know you can put that in a spreadsheet, and I know you could, but yeah, try to write. AISC has very beautiful design aids to look up column strengths, and if we were starting to do that with multiple column curves, I think those would become more complicated. Okay, I think that's a good stopping point today. So why don't we call it a day today? Unless there's any questions or any things you'd like to talk about, I'm happy to hang out a little bit more.